Hello, David. How are you today?
Good. How are you doing?
Good. Sorry about having a cold. I hate to miss seeing you guys, but figure it's better than the option of spreading a cold, if not something worse. I haven't taken a COVID test, but I kind of doubt that that would be something I've got. But
Yeah, hope you get better.
okay, I'll go ahead and get us started. And like always, I like to open up in prayer. Let's start with that. So, dear Heavenly Father, Lord, I thank you for the chance to be working with each of the students in this course. I pray that the material that we cover will be clear, that it'll be interesting, and they will be able to see that this is going to be useful information that's going to help them in their time at APU, as well, and more importantly, in their future profession of their choosing. Pray that you would help them in their spiritual formation, Lord, that they can learn so many interesting and important things in Scripture and help them to be understanding the theological concepts that we want to be deriving from that and use them in our day-to-day life. Give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Well, it's always a pleasure when some of you reach out and are sharing your journey and doing the coding. It also helps me to know that maybe there might be some things that maybe I should be sure that I highlight. And so I'm going to continue to enjoy having that process of having you do that. I know it's a little bit different than the coding that maybe you've done up to this point. There's a little bit more latitude. There's more things that you get to be choosing how you want to be accomplishing your end goal. And so part of that is maybe just starting to get a sense of a strategy that works for you. And so, of course, I'm going to probably give you what works best for me, and it might be something that'll work best for you. But try and keep that in mind. If you do get a little bit stuck, I always talk about trying to go from working code to working code. And so, if you have a lot of code steps and you start to get one method that you implement, go ahead and start there and then start building it out in a more and more complicated way as you go. So, the chart that I have been using up to this point um, that describes the course and where we're at. So we've been introduced to a couple of possibilities that we can be thinking about: array and linked implementation. And we're going to see something interesting as we get into queue implementation as part of our lecture today. This idea of a circular array implementation or a linked circular linked implementation that will actually help to improve the utilization of the amount of resources that we're allocating for an activity. So that will be one of the things that will come up. We started to see this with a stack, and we're going to see it again with a queue, but just being mindful of how things are done in an array versus in a linked approach, it can help us understand, well, what would be the relationship between the top of the stack and the end of the array, for example, or the first element in a linked implementation. And the very end of the lecture, we'll get into this idea that we haven't really touched on, but this is something we'll be getting into in a couple lectures, is dealing with sorting. So let's go ahead and focus on the material that we're going to be dealing with today. And so last lecture, we introduced queues, decks, and priority queues. Now we're going to be talking about the implementations. And so I'll go through this lecture material first, and then I'll swap over to several video notes, which will probably be helpful for me to save my voice a little bit. So these are the things that we're going to cover in the chapter. And so we'll be bouncing around between linked implementation and an array implementation. And so the first thing is we'll get a chance to be thinking about a linked implementation of a queue. So now we have linked and array options. We have queue, a deck and a priority queue we have to be figuring out. And so those are a couple of things that we begin to get a little bit more complicated and more choices, more tools in the toolbox that we can be leveraging. So after we talk about a basic implementation of a queue, we'll first get into an array implementation of a queue that uses this idea of a circular array. And I think both in the video notes, and I'll try and leverage as best I can the things from the lecture notes that would be pointing out what that actually implies. And then we'll bounce back up to the linked implementation and talk about a circular implementation of that. Then we'll talk about a doubly linked implementation of a deck. And there's a nice graphic in the charts that I'll just be pointing out that could be giving you a sense of how this works. And the last item here is possible implementations of a priority queue. And actually what this requires is the ability to do some sorting, which we haven't really covered on. And so there's just one chart that we'll be referring to, but it'll give you a sneak preview of something that will be coming into in a short order. So here we see a linked implementation of a queue. And so the first node is over here, and this is the entry at the front of the queue. And so that's the one that we're always going to be servicing first. And then here we have the entry at the back of the queue. And so we're going to add things here. And so we're going to be placing a new entry between this point here and then point to that new node at the end of the chain. So that's just a general sense of this diagram that I think you probably have some familiarity with things that we've talked about up to this point for a linked implementation. So some of this is going to be familiar. So when we implement the interfaces, and one of the things that came up here, and I just wanted to remind folks that when you go in Eclipse and you implement a interface, there's a couple error messages that show up. And one of these things is you need to get these angle brackets T on both what you're implementing. In this case, it's going to be a queue interface, and the new name that you're coming up with, we're still using this helpful naming convention that we start out. If we're going to be doing a linked implementation, let's use that in our title of this, and so we call it a link queue. And so just as we saw in this previous chart, we want to keep awareness of the first node and the last node. So we have those two variables. We have a default constructor where we don't initialize either the first node or the last node, so they're empty. And we also have this private class node. So when we're doing a linked implementation, this is the typical way that we'll be seeing it implemented with a private class, a private inner class. So we're not showing a lot of details here, but there's still a couple of things that are worth pointing out. And one of the things that happens if you say you didn't put this angle brackets T, I haven't explored it in a lot of detail, but I think what this will happen, it will cause issues when you're trying to implement your methods. And so that's one of the artifacts in case you might be seeing that might be the reason. So let's look at the adding. And so for a queue, it's NQ. But the generic term we fall back to is just we're going to be adding or removing. So here we have this. And so we don't have this association. They started out with null. And so we're adding this new node and we're assigning it. It's the first node. And because there's only one node, it's also the last node. So this is how we're initializing our queue. So if we want to be adding one, this is the general process of what we're doing. And so here we're also showing you the type of code that we would be doing. So before the addition, we say have just one node, and now we're going to be having this new node we're going to be pointing to. So this is where we now have the new first node is now pointing to the old first node. And so and then we need to be fixing the association for where the last node is. And so the last node is also the new node. And so this is a temporary thing here. And if we had multiple things over here, we'd have the first node would be over here, kind of thinking like what we have on this type of a diagram. So when we're done there, we would have two nodes, assuming that before we got there, we just had one node as we're showing in this figure. So this starts to give us an idea of what we're going to, that we have a temporal variable new node. And so at the very end, we want to make sure that we update the association for the last node. And so last node is new node. And so this is how we create that association, the last node, and then we use a method of set next node and then we're setting that next node as the new node, and that's what makes this association with this we're seeing with that arrow. So this is the NQ process. And so we can see those lines of code that we had. The very last thing is we set last node as the new node. And as long as it's not empty, then we have this last node dot set next node of using the one that we've added. And so there's other things that we're going to be leveraging. We're not showing those private methods and stuff like that, but that just gives you an idea of how we do that implementation for an NQ. And so you're going to have this sample code, like the very first one when we were doing bags, you had a sample, the stack, you had to be doing more on your own. And what's going to be similar for a queue, the good news is with the implementation of the queue interface, we only have 5 methods we have to do. And so that's going to be a lot better than the built-in Java version, which I don't want people to do because we're trying to give a chance to have people get familiar with what it's like to program for the back end. That's where we're doing the implementation of this interface, and also doing front-end programming where you're doing what a customer would do with developing an application, assuming that you're trying to separate those two possible ways of programming. And so here we have the get front. This is like the peak for the stack. So first we have this useful thing to make sure that if it is empty, we want to be throwing an exception. You're asking me to do something, but there's nothing there. And then we return the first node, and here we have a method get data associated with that first node. And so that's this is one of the methods that it would be associated with the inner private class node. So this is the process of what we do for removing. And so basically you can see that we're getting rid of this this front end one. And so this one's going away. We're going to be transferring first node associated with what is B. So this is where like we're servicing the person that's in front of the line or in front of the queue. And then we provide back to the user the value associated with the initial entry here, and so that's returned as a something that comes out to the client, and after that it's lost, and so there's no more of this first link in this chain that existed in the beginning, and so thus we go from a line of 4 to a line of 3 when we do that that removal of the front person in line. And this is what we have here. And so it's DQ. The first thing is we have to initialize the front. So we get what the front element is. we then take away that value, but we've kept the front in a temporary value. Then we associate the first node with the get next node, and so that's now it's associated with the second element. And if it's a first node, we don't have to, then we know that the last node is equal to null, and then we return the front. And so thus we have the general case, and then we have the one specialized case if we have the first node. If there was only a chain of one, then we're going to go back and set the chain to null. And so it's going to be initialized that way. So so this is before and after removing the only entry for a queue. And so that's just getting into a little bit more specifics of thinking what's going on with this extra if statement here. So that's just some more details that might help out. And then we just have two other simple methods, the is empty. And so we just return this is a Boolean. So first we want to see if the first node is identically associated with being null, and the last node is identically associated with null. And so we have to have both of these to be the fact that they're null before we can return that it is empty. So this is a little bit more, you could have just done one or the other, but this is a more rigorous way of verifying that it is empty. And maybe there was some subtle things going on in your code. And then clear, all we have to do, this is where for a linked implementation, a chain implementation, all you have to do is just get rid of these associations for the first and the end, and everything else just goes away. And so that's how we set that ready for the Java garbage collector to clean up. So that's I think that's the end for the implementation of a queue in a very simple manner. Okay, well now let's think of next think of an array implementation. And so we're using an array in the backend code for an implementation. And so basically for the front of the queue is at the beginning of the array. The end of the queue is towards the end of the array. And so here we have an array that has a size of 50. And so the index for the beginning is 0. The index for the back is 5. And that's what we have here. So if we want to remove the front two entries, this is what it's going to look like. And so now the front index is going to be 2, and the back index is going to be 5. And so we're going to continue to grow this array down at this end. But what happens here, we're losing access to this front of this array. And so it's not going to be a very efficient use of this linear array. So one of the strategies of dealing with this is to use what's called a circular array. So if you were just to bend this around, so item 49 is right next to item 0. And so what's happening is we're removing from the front and we're adding to the end. What it's going to look like is like the active elements are just going to be rotating. And so if we're removing here item 0, it's going to look like it's going to counterclockwise, and the elements that are vacant would be slowly moving in this direction. Well, what this is going to do is it's going to allow us to be using more elements in this array before we run out of array elements and don't have to do this resizing as often. So that's the strategy that we're seeing here. And hopefully you're picking up on what I'm trying to describe by going through these lecture notes. And then we'll see this again when we go through the video notes towards the end. So eventually we get to a point where things are full. We need to double the size of the array. But if we're actually in the situation and we're just trying to remove elements, if it was completely full, we take 2 out, voila, we don't have to resize. And so we're still fine, but that would be at the upper level of what we would have to deal with in this situation. This is just some more details. I'll just skip over this for now. With a less full array, you can see that. And so here is a circular array with one unused location. And so that's the implementation for that. And I think this is going to be easier to track with the video notes. I'm going to skip over these quickly for now, but I tried to give you a general sense of when we were going through the first circular array looking rather than showing it in a flat linear way. So here is for a circular array with one unused location. And so this is the implementation of dequeue. We're still having some nice code. And so in the beginning, if you want to keep things simple, this would not be necessary. You could just, but if you want to go in and copy and paste, just make sure that you don't get any typos. You may want to copy this out initially so that just to focus on the main elements. And a big key element that I wanted to really highlight is this modulo operator. And so maybe some of you like football, some of you may not. You could be thinking of analogies, but since we're getting close to the Super Bowl, you basically have a game that's 1 hour. And so 1 hour equates to 60 minutes. Well, actually 60 goes beyond what you can actually do in a clock. It's 0 to 59 minutes. And so this modulo operator is trying to keep you within that 60, if we think in terms of what it would be for a minute or for an hour by using this. And so this is how we can see a relationship between a clock, if you will, and the modulo operator. So this we would have it on modulo 50. My analogy of thinking of a football game with it being 60 minutes, we would want to keep it within below 60, so 0 to 59. And once again, the video notes will be picking that up. So if we need to double the size of the array, what we're going to do is we're going to take things out that we're taking advantage of that circular array and start with the first element being at 0. Here it was at 2, and so we'll put it there. So we'll take 2 to 0, 3 to 1, etc. And then we'll stick this very last one at the end. And so voila, we might as well go ahead and do that and reset it from the beginning. And so that's what we do in this method that we have, this private method, when we have an array implementation and we need to double the size of the queue. So this is the ensure capacity. And so we had this before, but there's a few modifications. And so now we see this modulo operator come up here, and this isn't something that we had. And so if you want to be looking at the old ensure capacity, and one or more of you have included this in your code, this would be one of those subtle things that you would want to add when you're dealing with a circular array. So I wanted to make sure I point that out. So here is the circular array implementation. When we're using, here's a queue implementation when we're using a circular array. And so this is once again where this modulo operator comes in. And so those are just a couple subtle things that we want to make sure that we're looking at. And we also can be having a circular linked implementation of a queue. And so this would give you an idea of what that would look like. And so Might be a little bit harder to wrap your head around that, but that's at least a top level figure what it would be. And so if you have a one node, then it's going to point back to itself. And so that just gives us some insight into how we would go about coding. And so here we can see we have 2, 4, 6 nodes in the chain. And so here we have 3 nodes that are available to the queue and 3 that actually have values in it. And so that would just give you a more rigorous way of seeing that. So here we have the first available node. Here is the front of the queue. And so that would be some things that would be helpful for us to start to get our arms around how this would work. And this is some more details that you can feel free to take some time to look over the textbooks or the lecture notes. I'm just going to skip over this for right now, may come back to that. So now we went over the implementation of an array, a circular array, and now we have a circular link chain implementation. And so here we have our constructor. We have that. We still have our private class node. That's something that we have to make sure that we implement here. And we're just giving some very top level insight of that here. So now we're into the queue process. And so we're going to be adding an element to the queue. So here is what we're going to be adding. So before we had 4, now we're going to have 5 elements. And so this is giving you a sense of what that's process is going to look like. These are some more details that I'm just going to skip for the moment. And so with those graphics, it will be a little bit easier for you to get a better sense of what's going on here with the circular linked implementation. So things are going to be connected to one another. This chain, it's basically a necklace. Maybe that would be an analogy that might be helpful for you to think about it. And you could rotate it, going from one element to another, but eventually you're going to get back to the one that you started with if you wanted. So now we're trying to do a necklace versus a chain if you wanted to use a word picture to give you an idea of what's going on. Here is the implementation of the get front. So that would be another thing that we want to capture. Here we have the DQ, streamlined with some leveraging the things that we have in the private class node that we're going to be using. And we have the is empty. And here we have the private is one of the private methods that we'll have is next node needed. And so it's basically a Boolean check to see if there is something, if there is a next node that is available or not. So I'm not going to go over this, but this is the built-in class, one of the built-in classes that Java has. And so we're not using this, but we don't have pull, we're not using element. And there's just more things that are here. We don't have offer. And so these are more methods that we're not going to be leveraging. And so why don't we just make something that's streamlined, that's specifically meeting our needs? And that's why we have the specific interface that we're looking at. So this is, if you want to get an idea for a deck, thinking about it for a linked implementation, this is what it would look like. And so normally, if you just had a queue, you would just have all the arrows going in this direction. And that's it. But basically, you could actually traverse going from the last node, going in the leftward direction, or going from the first node, traversing all the way in the right direction. And so this is what is going to be required if we wanted to do a deck implementation of a linked implementation of a deck. So here we can see things similar to the code that we already had, but there is enough of a distinction between this private class node that we're going to actually call it something else. We're going to call it a doubly linked node. That's what that stands for, doubly linked, like so we see here. And so we want to be tracking some more information here, the next and the previous. And so we need to be tracking this, that the connectivity going in both directions for each link in that chain. And so that's what we're seeing in that situation. Okay. This is just some more of the details that helps us to get a better sense of what's going on when we are doing that implementation graphically. And so this is for adding. And so we have the add to back. And so we have four things that we can do. We can add to back, add to front, remove from back. And so this is just one of those four things that we have to be doing for implementing a deck. So then we have the add to the front. This is what it would look like pictorially. And here is the code for add to front. And we have remove from front. That's what it looks like graphically. And here is what it looks like in the code. And then we have remove from back. That's what it would look like for the actual code. So I think this is the last chart. So we only have a very high level introduction to a priority queue. And so here we can see that each one of these is given a value. And so the highest priority is supposed to be at the front of the queue. And so with an array implementation, that would be the last element in the array. And so let's say we put in a value of 7. That means that I would have to put it right here. And so we have another one that's been enqueued. And so this would have to be moving to item 4, and then we'd have 7 be put into this array element number 3. That's what would be happening in that direction. And so with a linked implementation, it's actually backwards in terms of the implementation. So the highest priority entry would be the first node, while the highest priority entry in array would be the largest array element. So maybe this might be another way to help you get some more insight into what's going on between each of these implementations. So if I wanted to put in something that had a priority order of 7, I'd have to put it in between these two elements here. I'm not going to have to resort this whole array, but I'm just going to have to break in here and put a new chain right in that location. So let me check and see if there's any comments or questions on what I just shared. Thumbs up if that makes sense. I know it's getting a little bit more complicated. So next, let me move over to the video notes. And we'll just focus mostly on lecture today. So we'll have 3 video notes, and I'll do a little bit of commentary in between them. So let's go ahead and first of all talk about the link queue. Let me try and make sure I get my sound about right.
In this lecture, we implement the ADT queue using a linked chain. We'll call our class linked queue. Since we're using a linked chain, we need a node to reference the head of the chain. Let's call this queue front. So the head of the linked chain is the node at the front of the queue.
So we're declaring we're going to be having a private class node, and we're going to be queue front is going to be an instance of that private class node.
This means that we can quickly dequeue items since the head of the chain can be accessed faster than any other nodes. But if the head is the front of the queue, then the tail must be the back of the queue. If we only have a reference to the head of the chain, every n queue will be order n as we iterate through the chain to arrive at the end of the chain to link in the new node. We can improve on this by implementing a node that references the last node or tail of the chain.
So some of you might recall this, but this came up before when we started to look at linked implementation, that we get better big O notation performance when we have links to the beginning and the end of the chain. So that's what they just went through. Now we're putting it in the context for a linked queue.
We can call this queue back. By maintaining a reference to the last node, we can add new nodes to the tail of the chain in order of at most one. When we first create our queue, it's empty, so the references to queue front and queue back should both be null. And for our ADT queue methods enqueue, which adds an entry to the back of the queue, we need to handle an empty queue as a special.
So a constructor for a linked implementation is a little bit simpler. So here we have we don't have to be looking to make sure and ensure capacity and stuff like that. And so here we have a constructor that sets things to null, so there aren't any chains elements to begin with. And now we're seeing one of the first methods that we're looking to implement here.
Special case. We first allocate a new node and add it to the end of the chain. If the queue, and therefore the chain, is empty, we make both data fields, queue front and queue back, reference the new node. Otherwise, both the last node in the chain and the data field queue back must reference the new node. Our enqueue method only sets the data field queue front when the queue is empty, since when our queue has only a single node, that node is both the first, front, and last, back node. If the queue is not empty, enqueuing future items is straightforward. We create a new node to hold the item we're adding to the queue, then queue back is set to reference the new node, and then the process is repeated for each of the following items that we enqueue into the queue.
So this is what we've done before when we did it for bag and also did it for stack. Now we're doing it for queue. We see this graphic and then we talk about it, and then we could have translated this into pseudocode, UML, and then actually do this, but this is the code that is actually doing that functionality here. And so maybe if you want, you can pause the video or look at the lecture notes or the textbook and just see if you can see this translation. And so when you're doing your coding, hopefully it'll be a little bit easier for you to go through and make this work.
This operation is independent of other entries in a queue, and its performance is thus order of at most one. Now let's look at implementing getFront and dequeue. Our getFront method returns the item at the front of the queue. We get the front entry in the queue by accessing the data portion of the first node in the chain. QFront has a reference to that node. Thus, getFront, like in queue, is an order of at most one operation. Note that if the queue is empty, getFront throws an exception. Our client can catch this and act accordingly.
So, like what they said, we had try catch blocks, and it says you could give that information without killing the whole program and say back to the user, maybe you misspelled something here. So the queue is actually empty, and so maybe that would be kind of nice rather than having to, maybe you're going to lose some data because it crashes. So there's various possibilities. So we're seeing basically it's pretty simple. You just return, since we keep this as a variable, this is an internal variable. And so this isn't known to the client or user, but that's ultimately it's really maybe we could do this method in one line, but we're trying to be more better coders by allowing for this exception to help out.
Get front does not change the structure of the queue. Our DQ method must handle the special case of when the queue has only a single item. Let's see how DQ works and why we need that special case. After creating a variable to hold the value that will return to the client, we check to make sure the queue is not empty since we cannot return a value from an empty queue. We then set front to the value contained in the first node and increment queue front to reference the next node in the queue.
So this is operating like a line or a queue. So we take what's in the front, and then we're going to go to the next. And so we're dequeuing these one step at a time. And so these first one don't need this special case for this when there's only one element. And this is when we'll be getting to this if statement here in just a minute.
Other DQ operations will function similarly until we're down to a single node in the queue. We set front to the value contained in the first node, and then increment queue front to reference the next node in the queue as we did before. But now there's no other node in the queue, so queue front is set to null, which was the value in the first node's next data field. At this point, queue back still references the node that was at the front of the queue. This is not correct. There are currently no items in the queue. So we set queue back to null to reflect this. Since there's no references to the node containing the item turtle, Java's garbage collection can free that memory. There are several ways we could implement our isEmpty method. When the queue
So here's another thing. This, in case you don't remember, this is or. The two ampersands is and.
is empty, both queue front and queue back should be null. So we only need to compare one or the other to null and return the result. But if there's an error in our implementation, and for some reason only one of these have been set to null, it's safer to test or to compare both queue front and queue back to null. And if either's null, return to the queue as empty. The clear method is straightforward and involves simply setting both queue front and queue back to null, so that any references to nodes in the queue are removed.
Okay, so that's a first. And so what we were talking about here is let's go back to the first slide for this chapter. So we did a linked implementation. Now we're going to talk about an array implementation, and then we'll finally get a chance to be talking about like a deck and a priority queue in the third video, just a little bit here, but let's go ahead and now think about the array queue. So basically for your queue project, you can either do a queue, a deck, or a priority queue. Since there's most discussion on a queue, if you're not quite sure what to do, maybe just go ahead and do a queue. But I also just wanted to give you a heads up for what these more advanced type of capabilities are like. And you may now or in the future want to be leveraging those depending on what you're trying to have your code do. Okay, so now let's get into the second video note.
This lecture presents an array-based implementation of the ADT queue. If we use an array to contain the entries in our queue, we could let the array element 0 be the queue's front. Here, front index and back index are the indices of the entries of the queue's front and back respectively. As we enqueue items, they're placed in the element after back index, and back index is incremented. But what happens when we remove the front entry? If we insist that the new front entry be in array element 0, we would need to shift each array element by one position toward the beginning of the array.
So this would have been a possibility, or this way we wouldn't need a circular array, but its performance is going to be a lot less, especially as you get more and more elements, because every time you do an activity, you're going to constantly have to be moving it down to the beginning of the array.
This arrangement would make the operation DQ very inefficient, especially for large queues. Instead, to keep from copying the array entries each time we DQ an item, we can leave the other array entries in their current positions when we remove the queue's front entry. But as you can see in this example, after several additions and removals, we run into two problems. First, the queue entries have migrated to the end of the array. Our back index reaches the end of the array, so we're unable to enqueue any more items. The last available array location is allocated to the last entry added to the queue. We could expand the array, but the queue has only 4 entries. The second issue is that we have several unused array elements at the beginning of the array. We have no way to reclaim or reuse these with our current algorithm. Since most of the array is unoccupied, why not use this space for future additions? In fact, that's just what we're going to do next. Once the queue reaches the end of the array, we can add subsequent entries to the queue at the beginning of the array. We make the array behave as though it were circular, so that its first location follows its last one. To do this, we use modular arithmetic on the indices. Specifically, when we add...
Anybody have familiarity with modulo arithmetic or using that in coding? If you want to do a thumbs up if you have, and if you haven't, that's okay, but just want to get a sense. Okay, so this is new. That's perfectly fine. But this is an example of one of those things that you're picking up in this course that you could be applying in the future, and it has some interesting ways. And so we're not just learning how to do basic coding, we're actually learning some interesting strategies. And so this is one that can really be a time saver.
Add an entry to the queue, we first increment back index modulo the size of the array. For example, if Q is the name of the array, we increment back index with the statement back index +1 modulo Q.length. To remove an entry, we increment front index.
So maybe using my example, you can be thinking of like, well, there isn't, if you have a game that's 60 minutes, you can't say, 65 minutes or something like that. Or you can't say it's 25 o'clock. I'm using it that way. If I was using a 24-hour clock, it would 25 would actually be you'd have to subtract 24, so it's actually 1 o'clock to give you a sense. And so this is what we're starting to thinking about when we have the limitations of what our circular array can handle.
Modulo the size of the array in a similar fashion. Let's see how this would work. Currently, our array Q has 7 elements. Front index is 3 and back index is 6. For the next call to NQ, we increment back index using our formula, and so the item is added to array element 0. Each call to NQ uses the same formula to increment back index, but the wraparound.
So you have this one that's going in clockwise and this other one that's going in counterclockwise. And so we have two things going on in parallel. And I was trying to describe that when we were going through the lecture notes before we do this. But this gives you probably a better dynamic way of seeing it.
Only occurs when it reaches the end of the array. Front index will behave similarly with each call to DQ. Let's enqueue one more item so we can look at how to determine full and empty queues. Not using one array location allows us to distinguish between an empty queue and a full queue by examining only front index and back index. In Java, each array location contains only a reference, so we're going to waste very little memory by having an unused array element. Here we will leave unused the array location that follows the back of the queue, which in the queue's current state is the array element 3. When the array is full, the index of this unused element is always 1 less than the front index and 1 more than back index. We can test for a full queue using the formula shown here. Let's empty the queue by dequeuing all of the entries. We can see that after the last item was dequeued, front index crossed over back index and is now 1 greater than back index.
So this is one of the things I think the video does a little bit better to give you an idea of how you're going to be maintaining your indices and to make sure that your logic is able to manage this.
And we can use this formula to determine if the queue is empty. This array-based implementation of a queue begins with 4 data fields and 2 constructors. The fields are the array of queue entries, indices to the front and back of the queue, and an initial capacity for the queue that the default constructor creates.
So this should look fairly familiar, this code. We're gonna have to do a little bit of a modification to this, but this is the basics for where we're starting with.
Another constructor lets the client choose the initial queue capacity. The initial size of the array is 1 more than the queue's initial capacity to allow for the unused element in our algorithms. Back index is initialized to initial capacity so that after incrementing, the first item in queued is placed into element 0 of the array. Front index is initialized to 0. This ensures our isEmpty test returns true immediately after the queue is created. Element 0 will be the front of the queue immediately after the first item is in queued. So we do not have to have a special case in our enqueue and dequeue methods to handle empty queues. IsEmpty is implemented with the test presented earlier in this lecture. The method enqueue first calls the private.
So this is where we get this module operator popping up. I thought there was I made a mistake when we were just going over the constructors. There isn't a modification, but this is where we see some things that are a little bit different than what we've done in the past.
Method ensure capacity, which doubles the size of the array if it's full, and then places the new entry immediately after the last occupied location in the array. To determine the index of where the enqueue operation occurs, we increment back index, but since the array is circular, we use the modulus operator to make back index 0 after reaching its maximum value. The method getFront returns either the first element in the queue or throws an exception if the queue is empty. The method dequeue, like getFront, retrieves the entry at the front of the queue, but then removes it. To remove the front entry of the queue, we could simply increment front index. This step would suffice because the other methods would behave correctly. However, the object that was previously the front of the queue and is returned to the client would still be referenced by the array. This fact is of no real concern if our implementation is correct, but to be safe, dequeue can set that array element to null before incrementing front index. We increment the front index after the item is removed using the modulus operator to make front index 0 after reaching the end of the array.
So we see the module operator there, we see the module operator there. So there's a couple of different places it shows up. And we saw getting an idea of doing some good coding, maybe more than we have to clear things up.
Now let's implement the private method ensure capacity. As we saw in earlier lectures, when we increase the size of an array, we must copy its entries to the newly allocated space. We need to be careful here though, because the array is circular. We must copy entries in the order in which they appear in the queue. So before we step through the implementation of ensure capacity, let's look at how we must copy the items into the new array.
So you might remember we had a diagram that was showing you that. We'll get a chance to see this again here. So go into full screen mode for this for a second. Yep, this one. So this is what we're going to be doing, this straightening it out and making it the first element. We're going to see the code for doing that.
Here we have our original array and the new array with double the capacity. Our old array has references to the front index and back index of the queue. We want to make sure that these are copied in the correct order to the new queue. The variable index will track the location in the new queue where the next item is to be placed. We use an increment front index as a reference to the next item that must be moved from the old queue to the new. When front index reaches the end of the array, it must wrap around to the beginning to find the next item. So we again use the modulus operator in our formula that increments front index. After all the items have been copied to the new array, we set front index to element 0 of the new array, and back index to the last item copied, which should be at element old size -2. In this example, the size of the original array queue was 7. That means that it can hold 6 items since we're leaving one array element unused. If we copy those 6 elements into a new array, the last item copied has an index of 5. So back index is the old array size -1 for the unused array element, -1 again for the offset in the array indices. Now we're ready to implement the ensure capacity method. We only need to increase capacity if the queue is full. So we check this first using the formula we discussed earlier. We then create the new array. We use a for loop to iterate through the old queue and use the modulus operator when we increment the front index. And finally, we set the front index and back index to reference the correct elements from the new.
So we spent more time going over notionally how this works, so not so much going through the code, but anything that we show in these lecture notes or video notes are in the sample code that is shared with you, so you can get a chance to look at this in more detail whenever you'd like. Okay, well, we talked about a linked and an array implementation. Now let's talk about some of the other implementations that we've got a chance to get introduced to in this chapter. And so we'll finish up with this video now.
In an earlier lecture, when we planned the link implementation of the queue, we noticed that the front of the queue should not be at the tail of the chain of linked nodes. If it were, we would have to traverse the chain to get a reference to the preceding node so that we could remove the queue's front entry. Although placing the front of the queue at the head of the chain solved our problem, such is not the case for a deck. We must be able to remove both the front and the back of a deck. So even if
So we're describing another tool. This is maybe you could still roughly say it's part of the queue family, but now we have this more capable deck, and then we have a more capable priority queue. And so in the future, when you're faced with trying to figure out, well, what data structure, what abstract data type are you going to be using, try and keep some awareness of this so you can say that, well, yes, in this application, a queue is not going to do exactly what I would want. If I was to implement a deck instead, what it still can do everything that a queue can, but it also gives me some additional capability, then go ahead and do it with a deck.
the deck's front is at the head of the chain, the deck's back will be at the chain's tail, and therein lies the problem. Each node in a chain references only the next node. Thus, a chain with its head reference permits us to begin at the first node and move ahead from node to node. Having a tail reference lets us access the last node in the chain, but not the next to last node. That is, we cannot move backward from a node, and this is just what we need to do to remove the back of a deck. What we need is a node that can reference the previous node as well as the next node in a chain.
So you can see there's more information that's associated with each node. Now you're going to have the data, but you're going to have the previous and the next. And so that's why having that private class node, and there was this, they called it DL node, which I shared before we got into this video note to see that this is what's going to be in each one of those nodes.
We call a chain of such nodes a doubly linked chain. We sometimes will call an ordinary chain a singly linked chain when a distinction is necessary. While an interior node references both the next node and the previous node, the first and last nodes each contain one null reference. Thus, when traversing the chain from the first node to the last, we'll encounter null when we reach the last node. Likewise, when traversing the chain from the last node to the first, we'll encounter null when we reach the first node. How do we define our doubly linked node? We can make our node generic so it's able to store whatever type of data we need. We're going to use 3 data fields. Data is a reference to an object of the generic type T. Next is a reference to the next node in the chain. And previous is a reference to the node prior to this one in the chain. If this is the first node in the chain, previous should be set to null. The constructor we'll use most in our DEC implementation takes 3 parameters. The first is a reference to the node that will come previous to this one in the chain. The second parameter is the data to store in our doubly linked node. And the third parameter is a reference to the next node in the doubly linked chain. We'll need an extra assessor method for the data field previous and an extra mutator method to set the data field previous.
So you can see that there's more capability than just a queue. And so we're just trying to outline that here. Maybe you've heard the term setters and getters. That's a general term. We heard different things for bag, for stack, and now queue. So setter terms is just a set as to add, if you will, and getter is just you're trying to sample it. So maybe a peak would be another example of something if you've already bumped into.
The doubly linked implementation of the DEC begins much like the linked implementation of the queue given in an earlier lecture. The class has 2 data fields, DEC front and DEC back, and the default constructor sets both of these to null. The implementation of the method add to back is like the implementation of in queue given in the lecture on the linked queue. Both methods add a node to the end of the chain so that our chain's current last node references this new node. Here, the new node is created, and we make it reference the current node by passing the DEC's data field, DEC back, to the node's constructor. This is what the DEC looks like after the node has just been created, but before we're finished adding it to the doubly linked chain. To finish adding it, we need to set next on the node that is currently the last node to reference this new node. Then set DEC back to reference the new node. The add to front method is similar in that it sets the next field of the node being added to DEC front when the constructor is called. So when our new node is created, it is already partially linked to the chain. We need to set previous on the old front node to complete the double link. We can then set DEC front to reference the new node added to the front of the DEC. The method remove front has an implementation much like that of our DQ method in our linked queue implementation, but it has an extra concern.
So this is something that'll start coming up more as we get towards the end of the book. There can be some differences between the sample code that is shared with you in Canvas versus what's going to be done here in the video notes. The video notes is actually from an earlier version of the textbook. This isn't quite what's being implied here, but we're starting to see a little bit of some divergence. And so you can sample both of them and make your own decision, which you feel more comfortable. Either one would work. But as time has progressed, the authors have decided to change their code. And so thus we see a couple possibilities.
After detaching the first node, if the DEC is not empty, remove first must set the data field previous in the new first node to null. We begin by saving the data stored in the first node so that it can be returned to the client. Then we increment DEC front to reference the second node in the chain, which will be the new first node. To completely sever the first node from our doubly linked chain, we must set the previous data field of the node that is now the first node in the DEC to be null. The method remove back has an implementation that is much like that of remove front, but after detaching the last node, if the DEC is not empty, remove back must set the data field next in the new last node to null. We begin by saving the data in the last node so that it can be returned to the client. Then we decrement DEC back to reference the next to last node in the chain, which will be the new last node. To completely sever the last node from our doubly linked chain, we must also set the next data field of the node that is now the last node in the DEC to be null. Okay, so a lot of interesting material that we've covered today.
And so that's it for the lecture and the video notes. And so Thursday, we'll continue to have our lab time. We'll focus on stacks, and if there's any questions that you guys have on that. And then as we start to get finished with that, we'll transition into going over some code for queues. But in terms of the lecture, we've covered the material on the queues. And so the lab is going to be lagging a little bit behind. And also, this is about the time I can start to let some of you share some of your code if you'd like to share it in class. And I'll tend to defer to having some time on Thursday for that. So any other comments or questions from today? All right, well, God bless you all. Keep reaching out if you have anything you wanted to dialogue, and I'm happy to do that. Okay? God bless.
Thank you.
Thank you.